In this video, we're going to talk about one-sided limits. So in section 1.1, we learned about 3 different ways that limits could fail. The first way was that the function approaches values from the left and the right, and they don't line up, right? That was one of the ways a limit could fail. The second way is that the function grows without bound. And the third way is that, you had oscillation near the point of interest. Now, today we're going to talk about the first of those 3 scenarios where we're approaching different values from the left and the right side. Okay? In section 1.6, we'll talk about how functions grow without bound and infinite limits. Okay, but for today, we're going to focus on this one where we're approaching different values from the left and right side, hence the one-sided limits. All right, so let's start off with a definition. Limit of x is x, the limit of a function f of x as x approaches c from the left is the left-handed limit of f at c is L is denoted here. You notice you're approaching c from the left. So I think about it kind of like a number line. In the middle you have 0. Over here you have your negative numbers like -1, -2, -3. Over here you have your positive numbers. So your positive numbers are on the right side. Your negative numbers are approaching it on the left side. So that's why they had that negative and the kind of like an exponent, but it's a negative, okay, on that C. So that's how I think about it, all right? So you're approaching from the left-hand side, okay? So that's the notation that you'll need to look out for. Now, we only consider values of x to the left of c, not the right of c. That's as x approaches c from the left side. That's the left-handed limit. Okay? The next is the right-handed limit. All right? So the limit is x of f of x as x approaches c from the right side. You notice the right side has a plus here. Okay? So emphasis here. You've got a plus, okay, a plus sign on the as your exponent on the C there. All right, so that's the idea. The positive side, okay, of the number is the right side. So we only consider values of x to the right of C. So you're talking about that number line. You got C there. We're only looking at numbers over here on the right side as we approach C on the right. That's the plus C side, okay? Whereas over here, numbers approaching C on the left is the negative C side, okay? Limit from the left. Okay. So let's take a graph, and we're going to do a piecewise function. These are perfect for these types of problems. So I have a line with slope 2/3 going through the origin, and this is valid for x less than 3. So x less than 3 is here. And so where is that true? That's true right there. And we have an open circle because it's strictly less than, no equal to sign in there. Now, the second part looks like an upside down parabola, a sad parabola, since the A term is negative. And so it's solid dot on the end at the 3 because it's got the bar underneath, so less than equal to, or greater than or equal to, rather. So when you graph this, you can use your calculator, or you can just graph the whole parabola and then take off the part that you don't need. And so if you do that, then this is what it will look like for you, okay? Now the question becomes, what are the left and right hand limits at, and it looks like we're probably going to do for x equal to 3, right? So, because 3 seems to be our critical point here. Now, the left side is this blue curve here. So to the left, numbers that are to the left of 3 are going to be less than 3. The right side looks like it's going to be greater than or equal to, okay? So greater than or equal to 3 here, okay? So let's do this one right here. This limit right here, we see what? What do we see that tells us what type of limit is? It's the limit as x goes to 3 from the left because of that negative superscript going on there, okay? So that means if it's from the left, I'm using this equation here. Bless me. All right, so I'm going to plug that in for my f of x. And so everywhere I see an x, I'm going to put in a 3. And when I do this, what do I get? I get 2/3 times 3, which gets me 2. And so does it make sense that this limits to 2? Yeah, I think so. That looks like 2 to me. So that limit is 2. Let's do, so it would make sense coming in from the left side. Like, let me do a little arrow here. Okay, so let's take this and I'm just going to move it around. So if I'm coming in from the left side, it looks like it hones in on 2. Okay? Now, the right-handed limit, see over here, I got the plus 3 going on. So this is the limit as x approaches 3 from the right of f of x. And if it's from the right, on the right side, it looks like I'm going to use the parabola curve. So to the right is x greater than or equal to 3. So if I do that, just using the little finger trick, if I take this here and I follow it in on the right, where does it look like it's going to level off at? That looks like 3. Okay, so this one's not going to have the same limit. So when I plug it in, what do I get? I plug in a 3 for x. I get -9 plus 24 minus 12, which gets me 3, which is kind of what I was expecting there. Now you can look at this and not think too hard about it and know that your limit as x goes to 3 from the left and x goes to 3 from the right is going to be two different things, because that looks like 2 there and that looks like 3 there, right? So what's the conclusion, right? What's the conclusion? Well, you could ask yourself, well, what about f of 3? What does f of 3 even equal? Well, f of 3, actually, if I plug in a 3, which equation do I use? I actually use this one because it has the equal sign. So if I plug in a 3 here, I've already found that, and that actually equals 3. So that is defined. But just because a function is defined at a single point does not mean that the limit exists here. Okay, so I wanted to make that point to you. Just because it's defined here at 3 doesn't mean that the limit exists. So what do you know about this limit here? Well, since the left and the right hand limits don't equal each other, then we say that the limits don't exist. So what do we conclude in general? We conclude this theorem right here. This theorem says that if we have f defined on an open interval, and the only way that we have the limit as x goes to c of f of x equal to some number is if and only if, which that's a fancy way of writing your little arrows. That means this is true if the next thing is true, but if the next thing is true, then the original thing has to be true. Okay? So, if and only if statement, it goes both ways on conditioning, right? So if the limit here is equal to L, then what does that tell me? That tells me that the left-hand limit equals L and the right-hand limit equals L. Now, something else that's useful is that if I know that the left-hand limit and the right-hand limit are equal, then that means that the limit is equal. So why did it not work here? Why did the limit not exist here? Well, we found that the right-hand limit existed and the left-hand limit existed. The left-hand limit was 2 and the right-hand limit was 3, right? However, they both were not equal to the same number, and because they were equal to different numbers, that tells me that the limit itself as x goes to 3 does not exist, okay? So not only do the limits have to exist, but they have to go to the same number in order for the limit as x goes to c to exist and be equal to L, okay? So just because you have a left and right hand limit existing doesn't mean that the limit at that same value exists, okay? However, if the left hand limit goes to a number and the right hand limit goes to that same number, then the limit as x goes to the number is equal to the same thing, okay? And then the other way around, if you know the limit as x goes to c of f of x is equal to L, then that tells you right there that the left hand and the right hand limit are also going to be equal to L2. Okay? So some pretty powerful things going on there. Your left hand limit or your right hand limit might exist, but it doesn't mean that the limit itself will exist coming from both sides. All right? So just a little trick of the trade for you.